Hello, welcome to the Exam 2 review videos. I'm going to start us off by giving you all some helpful suggestions for studying for the exam, and then we'll go handout by handout through what are some of the key things you should be watching out for. So let's start in with our study suggestions here. So study suggestion caveat number one is, of course, anything covered during class, in the as covered in class handout material, the associated homeworks and in-class quizzes is fair game for the exam. So that said, here are some study suggestions that I think will help you focus and fine-tune your exam preparation. First thing is make sure you've viewed and read carefully the Exam 2 information assignment on Canvas. So if we go to Canvas and we go to assignments and we look at our upcoming assignments, and we have here Exam 2 information. So you should read this assignment carefully and make sure it all makes sense to you. So that's number one. Number two, you should be sure that you can solve all the homeworks and in-class quiz problems from scratch. And then once you've done that, you want to make sure to review the concepts, definitions, formulas, handouts, and that will make sure you're not missing anything big conceptually that's important in any of the chapters. And then I would suggest watching this lecture and also the following part two. So those are the basics. And if you feel comfortable after having done these things, I think you're done and you should be in good shape for the test. If you feel like you need additional prep, here are some other things that you can do. You can solve the practice problems from scratch. I've got videos for the practice problems. They start with chapter 9 and go through chapter 11b. So I've got videos on each of these and also accompanying Excel files. Also, you're always welcome to participate and encouraged to participate in office hours. We have office hours now via WebEx, so you just go to Cisco WebEx and you can see the office hours that are coming up, mine as well as the TAs, and you're welcome to join any of those. Heads up that Nikhil is otherwise occupied, so he is not holding office hours, and we've been unable to take his notification down yet. So please ignore Nikhil's office hours, but Yuri, D, and I are all happy to have you. And also, you're always welcome to post questions to the discussions forums. Dee and Yuri and I all monitor these, and we try to answer your questions during working hours between 9 to 5, Monday through Friday. We try to answer those pretty quickly. And then finally, you can follow the How to Do Well in This Course guidelines that are in Homework 01, and they comprise the first question of Homework 01. So what I'm going to do with the rest of these two videos is walk us through the concepts, definitions, and formulas handouts for chapters 7 through 11b to make sure all of the concepts are clear and to give you some guidance on the types of numerical problems that you can expect to see. And again, as usual, the types of numerical problems you should expect to see are going to be very similar to the homeworks, the in-class quizzes, and the practice problems. All right, so let's jump right in with concepts, definitions, and formulas, starting with chapter 7. Okay, so let's think about chapter 7. Chapter 7 pretty much was just introducing some of the definitions that we've been using since in chapters 8 through 11b. A project, meaning for us a financial project, requiring some cash inflows and hopefully getting some cash outflows. Investment means same thing as project, and investor is someone who's evaluating a project. It could be a person or a group or an entity. And projects for us, financial projects, include a broad range of things, virtually anything that requires a cash outflow and hopefully will result in a cash inflow. So it could be buying a company, part of a company, a product launch for an existing company, making a loan, buying a bond, and investors include anyone who can perform a project or make an investment: hedge fund, mutual fund, private equity funds, individual CFOs, CEOs, company division heads, all that kind of stuff. And this is important. There are two fundamental types of investors, and these correspond to our two types of financial stakeholders: equity holders and bond holders. And the equity holders are the owners, right, or shareholders, and the lenders are the debt holders, bond holders, or those who hold loan contracts. And we use these definitions so we could get started with our discounted cash flow methods for project evaluation. And we needed these because things like, for example, balance sheet valuation, etc., what we've done so far, do not always work. But DCF methods always work, okay? DCF methods are going to work for any project, any participant. Remember, the balance sheet valuation method, we needed to have a balance sheet, and it was often difficult to estimate the market value of an entity's assets when it did have a balance sheet. Okay, that's it for handout 7. Let's jump on to handout 8A. And 8A was where we started out by deriving our fundamental time value equation, which says that the future value of cash is equal to its present value times 1 plus the interest rate that it's earning by, raised to the t, where t is time elapsed. And if we're looking at cash flow in and out of a project, we just rewrite that to say the cash flow we could pull out at the end is equal to what we put in the beginning times 1 plus our interest rate raised to the time elapsed. And then through the magic of algebra, we could solve this for the interest rate, or we could solve this for the present value, or we could solve this for the time elapsed. And we could also use natural logs, which are typically denoted like that. And either one is going to give us the right answer. So we sort of beat this equation to death algebraically, just solving for every possible thing we could. This is the only version of the fundamental time value equation that I remember, and then I just do the algebra as needed to solve for whatever I need to solve for. And we did look very briefly at simple interest rate, which we did not emphasize. And in general, we're always going to assume compound interest, unless it's specifically stated that this is a simple interest rate problem. Okay, so must be specifically Okay, so that has always assumed compound interest unless it's specifically called out that it's simple interest. Okay, we looked at graphically some of the differences between compound interest clearly growing exponentially, and simple interest grows linearly. And what makes our money grow faster? Two things as shown here. One is the more time we can let our money grow, the more money we're going to have. We have time here on the x-axis and the value of our investment on the y-axis. So that's one thing that helps us, just more time. Second thing that helps us is higher interest rate here. So we see with the 15% interest, our money grows much faster. Okay, and a few good things to keep in mind in a compound interest world, which is typically our world. Whenever our investments are guaranteed, cash truly is an exponential function of time. You can see it clearly on that graph. And for a lender charging R% interest, cash flow at t equals 0 is her cash outflow. She commits now to receive hopefully a bigger amount of cash back at the future time TF. For a borrower who's paying R% interest, cash flow 0 is the pile of cash that she gets now in return for her promise to repay a bigger cash flow at some time TF in the future. And we had some terminology which we've continued to use all the way through chapter 11b, and we will for the rest of the term. So when we're calculating R and we're going forward in time, we call that the interest rate. And when we're coming back in time, same R, mathematically the same quantity, but it's called the discount rate when we're coming back in time and solving for a PV. And the present value is sometimes called the principal or initial investment amount. Future value is sometimes called the amount that principal will grow to. Then we looked at cash flow diagrams. As you know, I'm a big proponent of cash flow diagrams, time on the x-axis, and for one participant in one project, we show the cash flows here. So these will be this participant's negative cash flows on the negative y-axis and her positive cash flows on the positive y-axis. And that was it for handout A. Let's go into handout B, 8B, and let's go to the beginning. And in handout 8B, we started to look at slightly more complicated problems that didn't just have two cash flows like this one, but now in 8B, we're going to look at general projects that may have many cash inflows and outflows. And we needed to figure out how to handle this type of problem. And the way that we did that was to say that the CF0, or PV tote, is always made up of these pieces. And one piece is associated with the first cash flow in the future, and another piece is associated with a different cash flow in the future. And we'd say something like this, our piece A and our piece B, we'd say the CF0 or PV tote is equal to A plus B, and A is equal to our 6K divided by 1 plus R raised to the 1 in this case, and B is equal to our 8K. Let me get the K's out of there. Divided by 1 plus R, same R, always 1 R per project. And so by breaking this PV tote into these pieces, all we're really doing for all these problems, and that's kind of true for everything we've done all the way through 11B, is just breaking up our big PV totes here into a sum of pieces associated with all the individual future cash flows. And notice how we always discount first when we're considering PV tote or t equals 0. Always discount first, then add them up. And on this page, I've just got in words what I just went over on the previous page, so probably a good idea for you to review all the wording on this page. And then we went from this simple 3 cash flow problem, 1 cash flow at t equals 0 and 2 future cash flows, and we looked at that and thought about that a little bit, and that led us to a general equation here, which we could use for any project that had a whole bunch of cash flows in the future, and we called that the fundamental discounted cash flow equation. So it says that PV tote, or CF0, is equal to, for each future cash flow I, discount it, do that for each one, for I equal 1 up to the number of cash flows n. Once you've got them all discounted, then add them up. So take each one individually, discount it back to t equals 0, then add them all up. That's all this equation says. So again, from a lender's perspective, PV total or CF0 is the amount we invest now, or we'd say the principal we commit now to receive the future stream of cash flows. And from a borrower's perspective, CF0 is the pile of money we can get now if we agree to pay the future stream of cash flows. So also mathematically, this future stream of cash flows, if you just add them up, forget about time value, all that, they should always be bigger than PV total. Why? Because from a lender's perspective, you're putting out a blob of money here and you want to get more than that back. So that's a good way you can always check your work with these problems. Okay, some math that we should know. If we have a PV tote situation like this, where we'd say the PV tote is 10, which is equal to 6 over 1 plus r plus 8 plus 1 over 1 plus r squared, we can multiply both sides by 1 plus r squared and get something that looks like this. And this is exactly finding going back to high school or grammar school, this is the type of thing where we're finding the roots of a parabola, and we want to use the quadratic equation for that. And in the equation to the right here, x is just equal to 1 plus r for us. So I haven't given you many problems where you've had to use the quadratic equation, but I have given you a couple, or maybe 3 altogether, all the way across chapters 8, 9, 10, 11a, and 11b. And then we spent a lot of time looking at constant cash flow project types, which are also called annuity projects. Okay, and that means the exact same thing. An annuity project is just a constant cash flow type of project. So what do we mean by that? We mean that there's going to be a blob of money going out. In this case, this would be from a lender's perspective at t equals 0. And in return for that, she's going to get a set of equal magnitude cash flows coming back, spaced at equal time intervals. And these appear all over the place in mortgages, car loans, financial annuities, with a little bit of modification. We see them in annuities due, and we looked at examples from all of these types of constant cash flow problems. And we developed some discounting cash flow equations for these. Our most fundamental one was that we just took our fundamental discounting equation and we said that if all the cash flows are constant, we can pull them out from where they'd normally be in here, just pull it out from the summation here and have that outside, which makes it easier to solve for. And we also got this formula, which was very helpful. The PV tote is equal to the cash flow. So remember here, C equals CF, just depends on the textbook that we're looking at, means the same thing. So the total PV at the beginning of the project is equal to this uniform cash flow times this whole mess involving R, and N again is the number of periods. And we can use this guy for any constant cash flow project, and we can use this guy for anything but annuities due. So and we'll have a slightly modified version of this formula for annuities due. And in general, it's really important that you understand how these diagrams work. So if we're a borrower, here we are at t equals 0, getting a big blob of money to help us buy a house or a shack or whatever. And in return for that, we pay a uniform series of constant cash flows, where here F1 equals F2 equals ... equals Fn equals F equals CF in our terminology. So from the borrower's point of view, you get the blob of money in return for making a series, equally timed series of payments of a constant amount. And from the lender's point of view, again, you give someone a blob of money in return for a contractual promise to get a constant payment back at constant intervals over time. And again, if we just mathematically, arithmetically add up F1 to Fn, that number better be bigger than F0 in this diagram. Otherwise, the lender is not making money. So that's a good way to check your work. And then we just took a moment here to think about risk. I just want to emphasize with you all that we should always be thinking about risk. And we just reminded ourselves that in general, interest rates increase with a project's riskiness. And there's no law of nature behind that. It's true because it's found to be true empirically. And we've agreed that the US Treasury can borrow money at about the lowest interest rates in the world, and it's considered, in quotes, a risk-free investment. As we saw in Chapter 9, treasuries are not really risk-free, but everyone calls them risk-free in quotes. And CDs are similar to treasuries because they're guaranteed by the FDIC. And in general, what we call subprime borrowers pay more interest than prime borrowers because they have a higher propensity to default. They're riskier. Okay, then we looked at annuity due projects, and annuity due projects are just annuity projects with repayments made at the beginning of the period instead of the end of the period. And they happen when a lender wants their cash back quicker, and very often when the borrower is paying upfront for each period for the use of the equipment or whatever it is during the period. So that could be an apartment where you pay your rent upfront at the beginning of the month. It could be a lease for a piece of medical equipment, something like that. Okay, so then we had some special formulas for annuities due. Okay, our general simplified fundamental discounting equation works also for annuities due. You just have to be very careful of making sure you've got the timing right of your cash flows. And then we got these versions of this formula that work only for annuities due. And it looks very similar to our PV-TOTE equation for annuities, except we have another term and things are a little bit different in here. And here's a nice, slightly further simplified version of this equation, which is good because using this one, using this version, we can find the uniform cash flow for annuities due, right? And then we did spend a little time talking about perpetuities, and a perpetuity is just a uniform cash flow project with repayments stretching on until hell freezes over, stretching on forever. And they satisfy this general equation, which has a problem because it goes out to infinity, but we found we could make a nice closed form equation for this, and this is definitely one you should know, that the present value of a perpetuity is equal to the uniform cash flow that's paid every year, every month, whatever the contract says, out to infinity, divided by the interest rate or the discount rate for the project. Growing perpetuities, we do not need in this course. So I'm not going to ask you about growing perpetuities. If, because of my early onset Alzheimer's, I do put a question of growing perpetuities on exam 2, I will just give everyone 100% for that credit. But I'm 99.9% sure I would not do something like that. Okay, so that was it for 8B. Then let's go on to 8C. And the ideas in 8C were, first of all, we wanted to think about how to compute far future values of cash flows expected in the future. And let me see if I have a cash flow diagram for this. I do. Okay, so this is good. So I'll leave it I'll leave it to you to review the wording here, and I'll just jump into this cash flow diagram. So what we mean by this is our far future values of cash flows received in the future is we're sitting here at t equals 0. We're going to get some cash flows at some time in the future, and each one of those cash flows is going to be growing by its interest rate r, and we want some time in the far future, which is t equal 3 here, to know what the total future value of all these cash flows is. So in this case, we're sitting here at t equals 0. We're going to get a cash flow in a year, we don't have it yet, of 25. We're going to get a cash flow in 2 years of 25, and we're going to get a cash flow in 3 years of 25. And the question is, how much money is going to be in our account a nanosecond after we get this cash flow of 25? Well, it's pretty straightforward. This one we get in a year, it has 2 years to grow. So we're just going to use the future value formula. The future value is equal to the present value times 1 plus the interest rate. We've said in this example, the interest rate is 9%, raised to the amount of time it has to grow, which is 2 years here. 3 minus 1 is 2, or you can just count from here, 1, 2. So how big is this one going to get? This one that we get at end of year 2 has 1 year to grow. So it'll be 25 times 1 plus r raised to the 1, and that grows to 27.25. The one we put in a nanosecond before we pull our money out of the account has no time to grow, so that's just going to be 25. Then we just total up everything that's in the account. 25 plus 27.25 plus our 29.7 for the 25 that's had 2 years to grow. We add them all up, we get 81.95. So that's what we're thinking about when we're talking about far future values of cash flows expected in the future. Very, very straightforward. Then the heart of 8C was really all about compounding periods. And everything up to 8C was done in annual compounding with r% interest per year, and t was a real number with the units, importantly, in years. So we had our consistent units, r compounding per year and t measured in years. And we want to be able to do monthly compounding, quarterly, daily, etc. And all we have to do to make that work is just consistently change our time units for, we want to change in r and in t, right, to make sure we consistently change those. So a couple of important things. So if we're establishing a quarterly compounding period, for example, we say r% interest compounded quarterly. That means this interest is paid every quarter, and we call this our native interest rate for quarterly compounding. And then in using this quarterly example, we're going to say that t equal 1 would mean 1 quarter from now, but in general, t equal 1 is going to mean 1 compounding period from now. So if we were working with monthly compounding, t equal 1 would mean a month from now. With semi-annual compounding, it would mean 6 months from now. And t equals 0 always means end of period 0. So here are some examples for native interest rates. So r equal 5% compounded annually. That's what we've done to date. R equal 6% compounded monthly. R equal 2% compounded quarterly, that type of thing. And then we developed this notion of the equivalent annual interest rate, or said in some text as just the equivalent annual rate. And we developed this because oftentimes in the real world, you're going to look at a project with, say, 5% compounded annually and want to compare it to a project with 6% compounded monthly. And how do you do that? There's no good way to do that without getting our compounding units and time units consistent across projects. And the EAIR is what allows us to do that. So let's look at its formal definition. So the EAIR is going to be the interest generated per dollar we have in a project irrespective of compounding period. So that's an awesome thing because now we can compare projects with R compounded monthly, projects with R compounded semi-annually. We'll just get the EAIR for all of them, and then we've got them in this apples to apples annualized basis. So what's our formula for EAIR? You need to know this. Start with your native R, right? Start with native R. Okay, and then you just say the EAIR is 1 plus our native R raised to the number of compounding periods per year minus 1. And then we had to sadly bring the nominal APR into the mix because it's used to advertise many consumer loans, and also it's used in many bond examples. So what is our nominal APR? It stands for nominal annual percentage rate, and it's defined to be our native R times the number of compounding periods per year. So again, this R here is our native R, our native interest rate. And we're going to say, sometimes you'll see just APR, sometimes you'll see nominal APR. For us in this class, if you ever see APR, we assume it means nominal APR. So here are some usage examples. If we have a native R of 7% compounded annually, we've got the, if we've got, our native interest rate of 7% compounded annually, our APR would be 7% times 1, or 7%, and we would describe it as our nominal APR equals 7% with annual compounding. If we have a native R of 10% compounded quarterly, then our APR would be 10% times 4, or 40%. And how would we describe it? We would describe it as our nominal APR equals 40% with quarterly compounding, okay? And knowing that, we can always get back to our native R by just dividing our APR by the number of compounding periods that are described in its definition. Okay, so APR is common but not usually helpful. So what we want to do whenever we see an APR is we want to convert it right away, convert to an R. First thing, convert it to a native R. We never want to put an APR in any of our time value equations. So convert it to a native R. What do? We just divide it by the number of compounding periods per year. That gives us our native R. And then we can compute an EAIR from that R, right, using our EAIR formula. Okay, and then we looked at an important application for both EAIR and APR, and that was bonds. And most corporate and treasury bonds are not amortizing, which we'll talk about a little bit later, but they do pay their interest twice a year. So that's important. And we looked at bonds issued in real-world bond markets under two circumstances: at issuance, and these are things you've just got to memorize. You've just got to know these definitions. So the principal of a bond is the amount borrowed per bond. The face value is the principal to be repaid at the end of the contract per bond. And for us, that's why it's going to be the same thing as the principal, and also heads up, that's called in some places par value. So for us, principal equal face value equal par value. And the coupon is the total amount of interest paid per year per bond. And we've got to remember that 50% of this is paid every 6 months. So we can get from the coupon a coupon rate, which is the coupon divided by the face value, and that's going to be given in that's going to be written as a percent. And once we've got all that in our pocket, at issuance, we can get the APR for the bond, which is always just going to be the coupon rate. So we describe that coupon rate exactly as we describe any other APR. So it would be X% interest compounded semi-annually. And then we can always get our native R for these bonds by just taking our APR, dividing it by 2, because we have 2 periods per year. And then we can find the EAIR once we have the native R, and that'll help us compare various bonds. And finally here, I know there's a lot of terminology here. In bond land, at issuance, the equivalent annual interest rate is called the yield to maturity. After issuance was the second time that we considered bonds like this, real-world marketplace bonds where interest is paid semi-annually. So after issuance, the purchase price of the bond is going to be determined in the marketplace. Okay, so it's not necessarily going to be equal to principal or face value. So we're going to have to, as a result of that, we're going to have to find our native R based on the current bond price and the contract stipulations. We can't find R from the APR anymore in general, and we're probably going to have to draw a cash flow diagram to find that R. Once we find the R, we can find the EAIR, and this is still same as YTM. And we looked at a couple of examples, but I think this is worth repeating here just to really hammer home how we have to think of things after issuance with bonds. So let's look at this one. On 112X1, Simple Company issued a bond maturing on 1120X7. Okay, so that'll be 6 years later with a $1,000 face value and a 10% coupon rate. Okay, so today it's 12X6. Okay, so they've just made a coupon payment and the bond is trading at 950. Let's find the native R and the YTM. And remember, the YTM is just equal to the EAIR. So what do you want to do with this? There's really nothing for it but to draw this cash flow diagram. Okay, we just need to think about what are all the cash flows if we buy the bond today. So if we buy the bond today, we're going to pay $950, okay, and we're going to get this bond has a 10% coupon rate, so that means it's going to pay $100 every year. But remember, the coupon is paid, 50% of it is paid twice a year. So that's how I got the 50 here. Okay, so 50 equals 100 divided by 2. And how did I get that? 100 is equal to 10% of 1,000. So that's how I got my 50. So we know that half of the coupon is going to be paid in 6 months, and the other half is going to be paid in 12 months, and that's the end of the contract. So that's when we're also going to get the contractual face value back. So here's our cash flow diagram, and now we would treat this just like any other 3 cash flow problem. And what we're missing here, what we need to solve for here, is R. We know the cash flows, we know when they occur, we've just got to get R. Okay, so I've got here the equation for R that I used to solve for R, and I found that R is equal to 7.769%, which you could get from trial and error just plugging into this equation. Just keep trying some R's until the right-hand side of this equation equals 950. Then you have the right R. If you're using Excel, which you can't during an exam, you could do a similar thing, but tell Excel to find it for you. Or you can use, as we looked at previously, the quadratic equation. And again, I don't expect that I'll give you a lot of problems where you're going to have to use the quadratic equation. But I think a good thing for me to ask would be, what would be an equation to use as a start point for finding R? and then this would be the answer to that question. And the way you'd get that would be by looking at this cash flow diagram. Okay, so once we have the R, we know the YTM is equal to the EAIR, we know the formula for EAIR, and we just plug that in, and so the yield to maturity would be 16.2%. And with the yield to maturity in our pocket, we could compare this potential bond to many other potential bonds. All right. And then in handout D was all about amortizing loans. So the notion of amortizing loans is whenever we have a uniform cash flow project, each portion of this uniform payment, some of each uniform payment is going to pay down the principal amount, the amount borrowed, and some of it is going to paying interest on that. And we've just never looked at it in that way before. So now let's go ahead and do that. And the key thing to remember here is that the right, the uniform cash flow is still going to be found with our formulas from 8b. Nothing changes here. So let me just go back to 8b for a second and find our formula for this. Whoops, here we go. So even though this is a we're looking at how this loan amortizes, we get the uniform payment, the relationship between the uniform payment and the CF0 or the PV total, the same way we always have. Nothing changes there. So if you're given a problem like this and you need to start with what's the uniform payment, just go back and use our uniform payment formula for that. And then what we did in the rest of 8D was make an amortization table for various loans to find the principal repayment amount that's hiding in each uniform cash flow and the amount of that uniform cash flow that is going towards interest. And so we started with a table with some information given to us and some not. We knew the interest rate in this case, and we knew how much was borrowed, okay? And then the loan payment using this formula, or because we already solved this for Mr. Small Net Worth, we could use what we already know, and we'd say the loan payment was equal to 12.063, and that's uniform. So that's going to be true in every case, and etc. And the interest amount is the BOP balance. Okay, so here's my beginning principal amount. So these two always go together, times 10%. So my interest is going to be 3.0, and the rest of that payment is going to be principal repayment. So let's go ahead and see how that looks here. So here we've got our uniform payments. So the interest, this is clearly 3 to 3 significant figures. Just have a little bit of rounding error in Excel, and I think that's because I don't have the 3 back here. And then 12.06 minus 3 is equal to 9.065, plus or minus a little bit. And we just keep going that way. Then the end of principal balance here is our 20.935 is equal to our 30 minus our 9.065. So every payment, the principal balance goes down by the amount of principal repayment. And for each payment, the total principal repayment plus the interest repayment equals the total payment that was made. And other thing, very important, at the end, after you've made your last payment, the principal still due at the end of the contract is 0. So you know if you've made one of these tables, if you get 0 here at the end, you've probably done everything right. And if you don't, you know you've done something wrong. And one of the last things we wanted to look at here is just show you how this is a 30-year mortgage here. So let's put that in. And you see in the beginning, almost all of your payment is just going to pay interest. You're not paying down much principal. And this is highlighted even better on this graph where we're just showing the payment of principal. And we don't even get to 50% until about year 25. So the lenders set things up that way on purpose. So if you flame out somewhere around here, they still have an awful lot of equity in this project. Okay, so that's it for 8D.